Have you ever wondered what's actually happening inside that little box when you connect to the Wi-Fi? Or, what all those blinking lights on your router are even for? Well, today we're going to pull back the curtain on all of it. We are going to build a computer network right from the ground up, piece by piece, explaining every essential bit of hardware as we go.
So here's our game plan. We're going to start with the one component that lets your device even talk to a network. Then we'll add the freedom of wireless. After that, we'll manage all the internal traffic, connect our new network to the big wide world, and finally, we'll look at the actual physical roads that all this data travels on. It's a simple, logical build. Let's get right into it.
All right, first up, the absolute foundation of any network connection, the Network Interface Controller, or as everyone calls it, the NIC. Just think of this as the passport and the official translator for your computer. It's what allows it to step into the world of the network.
Okay, so the thing you've got to remember is that a NIC really does two things. First, it creates that physical link, the actual plug for your Ethernet cable or the antenna for your Wi-Fi. But second, and this is just as important, it has to follow a super strict set of rules, called protocols, to make sure the data it's sending and receiving is actually understood by everything else. So it's both the plug and the rulebook.
Okay, quick question for you. We know the NIC is fundamental, right? But how has its actual physical form changed over the years? And what is its most essential, unchanging job? Go on, take a second to think about that.
And there we go. It used to be you actually had to buy a separate card and physically plug it into your computer's motherboard just to get online. Can you imagine? Now, they're so essential, they're just built right in from the factory. But its core job, that has never changed. Create that physical handshake with the network and make sure the conversation follows all the rules.
Okay, so our device is ready to connect. But really, who wants to be tied down by a cable anymore? Let's move to our next component and see how we can build some freedom into our network. Let's talk about the Wireless Access Point, or WAP.
Now, what's really interesting here is that word bridge. A WAP isn't some kind of magic box. It's really just a translator. It takes those radio signals flying through the air from your phone or your laptop, and it converts them into signals that can travel over the traditional physical cables of the network. It literally bridges the gap between the air and the wires.
All right, another question for you. We all love our Wi-Fi, right? But what do we give up for that convenience? And also, does a WAP in a huge office building work the same way as the little box in your living room? Think about those two parts.
And yeah, this lays it out perfectly. In a big building, you'll have tons of these WAPs scattered around, kind of like signal boosters, and they all feed back into one central system. But at home, your Wi-Fi box is usually an all-in-one gadget that's the WAP, the switch, and the router. But that trade-off is universal. Going wireless almost always means slightly slower speeds, and yeah, a few more security things to think about compared to just plugging in a cable.
Okay, so now we have multiple devices connected, some wired, some wireless. If they all start talking at once, it's just going to be chaos. We need a traffic cop, but for our internal network. And that brings us to our third component, the switch. The key word on this slide is intelligent. An older piece of hardware called a hub, well, it was like a person just shouting in a crowded room. It sent every single piece of data to every single device. A switch, on the other hand, is much more like a mail carrier. It actually learns where each device lives and delivers data only to the specific recipient that needs it. It's way more efficient and way more private.
So how does it do that? How does it pull that off? What's the secret sauce that makes a switch smart and lets it build that little internal address book of all your devices?
It's actually a really cool, simple process. Every time a device sends out some data, the switch takes a look at the from address. That's a unique hardware ID called a MAC address. And it basically says, aha, the device with this address is plugged into that port. It just makes a little note in its internal table, and over time, it builds a complete map of the local network. So the next time data comes in for that device, the switch knows exactly where to send it. No shouting necessary.
All right, our local network is looking good. It's organized, it's efficient, all our devices can chat with each other. But what about the rest of the world? To connect our little private community to the massive global internet, we need a gateway. We need a router.
And that is the router's one absolutely critical job, connecting separate networks. It sits right at the edge of your local network, your LAN, and it manages all the traffic going out to and coming in from the wider internet, the WAN. It's the bouncer, the receptionist, and the international shipping clerk, all rolled into one device.
Okay, this is a big one, and honestly, it trips a lot of people up. We just said a switch directs traffic. And now we're saying a router also directs traffic. So what is the core fundamental difference between them?
And here it is. This is probably the most important distinction to get. A switch is for local mail. It uses that physical hardware address, the MAC address, to send data between devices that are already on the same network. A router is for global mail. It uses the logical network address, the IP address, to send data to completely different networks, like a website server that's halfway across the world. So remember, switch is local, router is global.
We've got all our smart devices, the NIC, the WAP, the switch, the router. But how does the data actually travel between them? We need the roads for our information superhighway. And that brings us to our final piece of the puzzle, transmission media. This is pretty straightforward. It's just the physical stuff that connects everything together. For most of us, this means those familiar Ethernet cables, which are made of copper. But for the high-speed backbone of the internet, it means something way more advanced. Fiber optic cables that actually transmit data as tiny pulses of light. So let's think about that for a second. Why would you use a cheap, flexible copper cable in one place, but then a super expensive, high-tech fiber optic cable in another? What are the really core differences in how they actually work that makes one better for certain jobs?
And this table just lays it all out perfectly. See, copper uses electrical signals. Those are great for short distances, like connecting your computer to the wall socket, but they're vulnerable to interference and they lose their strength pretty quickly. Fiber, on the other hand, uses pulses of light, which are basically immune to electrical interference and can travel for miles and miles with incredible bandwidth. And that's why copper is perfect for your local LAN, while fiber is absolutely essential for those long-distance, high-capacity connections that make up the backbone of the entire internet.
So there you have it. From the NIC inside your laptop to the WAP for wireless, the switch for directing local traffic, the router as our gateway, and the physical media that connects it all together, we've built a complete network. So, which one of these pieces do you think is the most indispensable for how you use the internet every single day? The answer probably changes depending on what you're doing, but it's pretty fascinating to think about. Thanks for building this network with me today.